Hi, I'm Aaron Bestick, and I'd like to give you a quick overview of my work with Ravi, Pandya, Ruzena, Bajcsy, and Anca Dragan on learning human ergonomic preferences for robot-to-human object handovers. There's lots of existing work on object handovers, and most of it focuses on how we can make those handovers comfortable for robots-human collaborators, how we can avoid forcing them to twist or bend awkwardly to take an object. One approach that's been used in the past is to specify an ergonomic cost function for human arm configurations, then select a robot control that minimizes it, or perhaps minimizes it in expectation if we're modeling the human as a non-deterministic agent. In the past, we've just made up a cost function that seemed empirically reasonable. But this begs the question, how do we know this cost function is any good? Especially since we know there are differences between individual humans due to age, disability, and natural variation. What we'd really like to do is have the robot learn the cost function parameters online during interaction with each individual human. That's what we investigate in this work. Our insight is that we can treat the robot's action choice in each handover as an implicit query, and the human's chosen action as a label. Since we get to choose the robot's actions, we can choose those actions to maximize information gain. In this work, we compare the speed and accuracy with which we can learn human ergonomic models using two different query selection strategies. First, an active strategy, which selects the query with the largest expected information gain, and second, a passive strategy, which minimizes the expected human ergonomic cost in the current handover, given the ergonomic model we have currently. We compared these two strategies using 3 studies, and I'll show just a few selected results from those here. Our first 2 studies used a simulated human, where we could manually specify the human's ground truth ergonomic cost function parameters, then test each algorithm's ability to recover those parameters. In this figure, we can see the results of applying active versus passive query selection. Active selection on top results in a belief over the human's ergonomic preferences that quickly converges to the ground truth parameter values, shown by the green dot. On the other hand, passive query selection gets kind of stuck. It repeatedly selects the same query, even when it's no longer learning much from it. This results in a belief that's still quite uncertain, even after several queries. We see the same behavior when we compute summary statistics for each of our learned models at each iteration in our second study. In some cases, the passive query selection algorithm produces parameter estimates which diverge completely from the ground truth values. We also conducted a human user study where we saw similar results. There, we allowed the robot to choose both the handover configuration and the object to hand over. I'd love to chat more about our methods and results. Please drop by during the interactive session.